Hi, this video is an introduction to kinematics in physics. Kinematics is kind of like a branch of physics that is concerned with only measuring the motion of an object, not trying to explain why it's moving like that or how it's changing its velocity, just trying to measure the motion itself. And so far, as I've shown in previous videos, we have two foundational blocks of how we measure motion in physics. First, we have average velocity, which is the change in an object's position over time. We also have the acceleration of an object, so if its velocity is changing, the change in velocity over time is the acceleration. Now you should see some similarities between these two equations. Both of them are the change over time, and acceleration is the change in velocity over time. So we have some patterns here. But from these basic pieces, we can start to build out a larger toolbox of ways to measure the world. We get creative with it a little bit in physics. And already we've written some variations of these equations. So for example, instead of writing the delta v, the change in velocity, we can write that out as the final velocity minus the initial velocity over time. So this is one variation of the acceleration equation. There's also another variation where we could rearrange, really it's a variation of this one. We could rearrange the equation so that we're solving for the final velocity, because often we want to know how fast an object is moving after it accelerates. And so this is just a convenient way of writing that same equation above, but just, reformatted for us. But we can take it many steps further, and this is the first video of different ways that we can create new equations, new expressions that measure an object's motion. So let me show you the first one of these new tools that we can develop. Let's say we have an object that is speeding up here. It starts out at a velocity of 2 meters per second, and it speeds up all the way to 6 meters per second in a time of 10 seconds. Now, we could ask the question, okay, how fast is this object going on average? If the acceleration is uniform, that is, it's the same steady rate of acceleration throughout the whole, time frame that we're looking in, then we can find the average velocity just like we would find the average of any two values, where you add up the starting and the ending value and divide by 2. You add up the initial velocity plus the final velocity, and then simply divide them by 2 because they're two different values. This will give us the average velocity of an object as long as it's accelerating at a uniform rate. So 2 meters per second to 6 meters per second, if we add those two together, 2, my marker is not working too good, 2 plus 6 meters per second over 2, that's going to be 8 over 2, or 4 meters per second is the average velocity for this particular object. But this really comes in handy when we're faced with word problems like this. Let's say we have an owl that spots a tasty squirrel in a tree while flying at 2.2 meters per second. Let me draw my owl here. But let's find what the average speed of this owl is during his acceleration. So we're going to do the guess method. That's going to be givens, unknown, equation, substitute, and solve. So let's start by listing our given information using physics symbols. So the initial velocity, VI, is 2.2 meters per second. And then the final velocity is 5.7 meters per second. And this all happens in a time of 1.5 seconds. Our unknown information here for the first question is, what is the average speed? So we can use an equation for average speed that we just derived, and that is the average speed is the initial speed or velocity plus the final velocity, all divided by 2. This is only possible if the acceleration is uniform, which in most cases it will be for the scope of our class and the problems that we do. So to substitute in our numbers now, we have 2.2 meters per second plus 5.7 meters per second over 2. So the average speed here is going to be 7.9 over 2, 7.9 meters per second over 2. So when you put that into a calculator, you get 3.95 meters per second. However, our answer needs to have 2 significant figures in it, so I'm going to round that to 4.0 meters per second for the average speed of the owl. This allows us to answer the second question, so I'll draw kind of a line here and answer the second question, which is, how far did the owl travel during this time? Now, this is a tricky question because it's speeding up, so each second that passes, the owl is going even faster. Every moment that passes, he's speeding up, so he's covering more and more distance each second. So how would you go about figuring out how far total he travels during this speeding up time? And the easiest way to do that is to use our newfound average speed. So we already have all of our given information. I'll write down our new unknown information, which is the distance traveled. How far does the owl go, or is displacement. So we use delta x to represent how much the position changes. The equation we can use now is going to be this average speed equation that has the displacement in it, delta x over time. Okay, but we're going to rearrange this equation to solve for the distance traveled. This marker doesn't work. So I'm going to multiply both sides by time here. And so our displacement is the average velocity multiplied by the time. This is our equation that we can substitute into now. So our substitute step is going to be an average speed of 4.0 meters per second multiplied by a time of 1.5 seconds. And that's going to give us a solved answer. Got to include my S here. A solved answer of 6 meters per second. We need 2 significant figures. So 6 meters, not meters per second, meters. That is how far the owl travels. So that's all I've got for you in this video. Remember, everything you have is a gift.